So hello all. So we will be discussing about the problem number 4 here. So in the problem number 4, we will be trying to model the rolling process in a simplified manner. So the rolling process, we are having a sheet of some thickness, and that thickness will be reduced when we are passing this material over a pair of rollers. So let's look at this process. The initial thickness of the sheet is given. It is 31.25 millimeter. So if we look at the thickness of before enter into the rollers, this thickness, it is given as 31.25 millimeter. And if you look at the final thickness, it is given as 25 millimeter. So now what else the data is given? And the data given is roller diameter is given. So then let's look at the radius of the roller. It is 500 by 2. It is 250 millimeter. So it is R250. Then whenever the sheet is moving through the rollers, you will be having this area where the sheet will come in contact with the rollers. So there is a relative motion between the rollers and the sheet. So there we can assume it is friction. So the frictional coefficient is given in the question is 0.5. Then the rotation speed of the roller is given. The rotation speed of the roller is given. It is the top one is rotating in anti-clockwise direction, and that rotation speed is given as 150 rpm. So this is the physics of the problem. What we need to find out, we need to find out the roll separating force, because whenever the sheet is moving over here, you will be having some force will be acting on the rollers from the sheet. So this is the direction of the force from the roller, from the sheet to the rollers. So the roller is rotating over a bearing. So the bearing should be able to withstand this load. So that is what we need to find out from this problem by using the FEM. So let's look at how we are able to model this process. So what we are going to use it, we are going to use the symmetry of the problem. If you look at the center line in the horizontal direction, so you are having a center line here. So with respect to the center line, if you look at this problem is symmetric. So what we are going to model, we are going to model only the top part. So whatever, if you look at any point, if you are going to look at here, the point A or the point B, if it is a mirror, if B is a mirror image of A with respect to this one, then whatever happened to the A will be same to B. So we can find it out that one. So we are going to model only half of the problem. We will be using the symmetry of the problem. So let's look at what we need to model now. So what we need to model. So you are having the sheet. We will be modeling the sheet like this. It is coming like this. So this is a condition. Then you are having the center line. You will be having the center line like this. So then if you look at the thickness, before entering into the rollers. So this thickness is equal to, it is 31.25 divided by 2. So which indicate that 15.625. This is what you are going to get it. And if you look at the thickness here, when you look at the symmetry of the problem, it is 25 divided by 2, it is 12.5 millimeter. So we are just using half of the problem where we will be using the rollers. So then you look at the rollers, you are having the roller here. The roller we will be having here. This is a roller. So roller will have a center here. So this is what we are having here. Now the roller radius is given as is R250. So this is what we are having the data. So how we are going to model this one? We will be modeling this one. So when you look at the boundary condition, if you look at any point along this line, if you look at any point along this line, the symmetry boundary condition can be applied. And in this condition, symmetry boundary condition is the displacement along the y-axis. So in abacus, it is represented by U2, and that will be equal to 0 along this line. So that symmetry boundary condition we can apply over this line. So this is the area where we are going to use the symmetry boundary condition when we use the symmetry boundary condition when we are going to use the symmetry of the problem. So this is what we are going to model. Now we will look at, we are going to model 2 items. So the part 1, it is a sheet. Part 1 is sheet. So which have a dimension like this. So this dimension is 15.625, and this dimension is 12.5. Then this arc, this is an arc which is a radius of r 250. So length, it is not given in the problem. Let's say I am taking the length is equal to 200 millimeter. Then which is the next part? Just look at the next part. So next part is a roller. That is like a part 2, which is a roller. So what is the peculiarity to the roller? Roller have a radius of 250 millimeter. The radius is equal to 250 millimeter. And then what else is given? What we can assume here that compared to the deformation of the sheet, the roller will have higher stiffness, or the deformation of the roller will be negligibly small. So because of that one, we will be consider roller as a rigid body. So roller we can consider as a rigid body, and we are going to model the roller as a rigid body. Now when you look at the part sheet, it is a deformable body. So this we call that is a deformable body. This is how we can model this rolling process. So now when you look at the material properties, so what we are going to assume, the material properties, we will be assuming that it is, so let's look at the material properties. The material properties, we will be assuming that the material is elastic, perfectly plastic. So when you look at the stress strain behavior of elastic, perfectly plastic, sigma, sorry, it is epsilon versus sigma. So the material will have a behavior. So initially it will have an elastic behavior. So if you draw the stress strain graph, and the slope will be equal to the Young's modulus. The slope will be equal to the Young's modulus, and which is given here 10,000 megapascal. Then Poisson ratio, it is 0.3, which is given, and the yield point is given. Yield point is given in the question. The yield point is given as 100 megapascal, which is also given in the question, 100 megapascal. Then what we are going to do, the material is perfectly elastic. So whenever we are going to have the material is perfectly elastic, once the stresses reaches the yield point, sigma y, stress strain graph, if you look at, it will become horizontal. So this detail has to be entered in abacus about the plastic region. In the elastic region, we will be entering Young's modulus as well as a Poisson ratio. Now, when you look at the plastic things, so at 100 megapascal, you are going to have the yield strength until you deform the material. When you deform the material until the yield point, the plastic strain, let's say we represent the plastic strain is epsilon p, that will be equal to 0. And we have to draw a horizontal line. After that one. So we will be specifying the different points of a horizontal line. So the first point is 100 megapascal and the plastic strain is 0. In the second point, we will be having a small increment, let's say 100.1 megapascal, and we are going to assume that the strain is equal to 1. So even though it is perfectly straight line, we will be having a small inclination which can accommodate this perfectly partial behavior. So that is why we just increment a very small value from the yield strength so that you will get this points of a two different point of a straight line. So you are going to get 2 points of a straight line. One is 100 megapascal, zero plastic strain. The second one is 100.1 megapascal with strain is equal to 1. So when you look at and how we are going to model solid homogeneous. And when you look at the roller, so we don't need to define these material properties of the roller because it's a rigid body. This is what we are going to do. So now look at here, we will be creating this geometry. So I will create the geometry like this. So I will initially create this one. This will be clear whenever we are going to show the details in the abacus. So let's come back to abacus. Let's come back to abacus. So what we need to create two items. One is part 1, which is representing the sheet. So we are having the sheet. So how we are going to model it? Essentially, it is a 3-dimensional problem. We are going to model here by using a 2-dimensional problem. So that is what we are going to do, sheet. So we are going to model 2D planar. So then you are having deformable body. Then you are going to create shell. So the geometry which we are going to enter here, it is in millimeter. Finally, we can get the stress in megapascal. So we will be entering the details. If we come back here, the units which we are going to follow is not SI unit. The units which we are going to follow, let's come back here. The units which I am going to enter now in abacus, the force I will be entering in Newton. Then the mass, if it is there, I will be entering in kilogram. Then length I will be entering in millimeter. So then time I will be entering in second. So that finally I am going to get the stress in megapascal. So when you look at the geometry, all the geometry parameter, we will be using the units as millimeter. We will not use meter. Now, when you look at the Young's modulus or yield strength, we will be entering in megapascal. So it is essentially, if it is, let's say sigma y is equal to 100 megapascal. This is essentially 100 into Newton per millimeter square. That is what you are going to get it. 100 Newton per millimeter square is 100 megapascal. So in this case, force, it's unit of Newton and the length unit in millimeter. This is what we are going to do. And whenever you are going to specify any dimension, you are going to specify in millimeter. That is what we are going to do. So come back here. So we will be specifying in millimeter. Let's say we are using 200 itself. So coming back here, we will be creating a rectangle. So let's say the 2 points of a rectangle, one is origin 0, 0. Then the second point, it is minus 200. So minus 200, comma. The y coordinate is 15.625. This is how I am going to create the rectangle. So these rectangles and roller will be created in such a way that you don't need to do any additional operation in assembly. In assembly, you have to bring this plate as well as a roller in the correct position. But that can be avoided if you are going to create geometry according to this method. That is the advantage of this one. So I am going to create a rectangle which have a length of 200 millimeter and the width of 15.625 millimeter. So if you look at the screen fit, you are going to get the rectangle like this. So what we are going to do now, I have to create an arc here. So essentially I will create a circle. So when I am going to create a circle, the center point of the circle I will create in such a way that I am able to get an arc in the specified point. So the center point of the arc is 0, comma, then it is 262.5. That is the center point of the circle. So I got the center point of the circle here. Then after that, what we are going to do, we are going to create a circle then I need to specify a point in the perimeter. So then the perimeter point is actually 250 millimeter from the center. So what we are going to do, it is going to have 0, then it is 12.5. There I will create. So now you can see this is, I got a circle. Let's look at the geometry of the circle. So you can see we are having a radius of 250 millimeter. And if you look at this distance, if you look at the distance between these two things, so let's say this point is more. Then we will take it, we will check it later. So what we need this geometry. We have to take this arc and we have to remove the remaining part. So for that one, we will be using this parameter, which is called auto trim. So when you are using auto trim, we will be removing the unwanted portion. This I will remove. Then this point I will remove, and this point I will remove. So let's look at whether my geometry is correct. So this is 200 millimeter as per my requirement, and this is done. Then this is 15.625. This is 15.625 as done. It's you can see it at the bottom, 15.625. Then look at this dimension. It is 12.5. So our geometry is completed. Even if you look at this, the circle, it is 12.5. Then look at this one. So it have a radius of 250. So everything is set now. So our geometry is correct. So we will be finishing this operation. Done. So the plate is created. Now we have to create the roller. So whenever we are going to create the roller, what we need actually, we are going to create 2D planar. What we are going to create, it is roller. So then you are going to create a 2D geometry. Then what is the peculiarity here? We are going to create a rigid body. So we will be going for analytical rigid bodies. Then you are able to create the roller, which have a radius of 250 millimeter. So approximate size is 250 millimeter to 200, or let's say we call it as 250. So done. So you can, what you can do here, you can just draw a circle. So you can just draw a circle. So what is the peculiarity of the circle? Which have a center point is equal to 0, same as center point last time, 262.5. That is the center point. So center point is located here. Then which is the perimeter? Same as earlier. It is 0. Then y coordinate is 12.5. So you got a circle like this. So this is the roller in our case, but Abacus generally will not allow us to create the rigid body like this. Let's check that one. So let's say we have completed. We will try to done. So you can see Abacus is giving a message that an analytical rigid shell sketch may contain only lines, circular arcs of lines or circular arc of less than 180 degree. So only circular arc of less than 180 degrees permitted. So then we will be removing the part which we does not require. So we will be coming back here. So what is the portion which we require? We need this portion. So what is the portion we require? We need to less than 180 degrees. So this is 180 degree. So I will take it less than 180 degree. Then cancel. Then I will use the trim command. So I will remove this part. I will remove this part. I will remove this part. So then it's cancel procedure. We have created an arc which is less than 180 degree. So done. So we got the roller like this. Roller is defined as a rigid body. So then what is required now? The parts is created. So another thing we can do actually, if we want to assign the rotation of the roller, and if you want to assign some boundary condition of the roller, because that has to be done during the process, because roller center point, you have to constrain the displacement, and the about roller center point, you have to rotate the roller during the rolling process. This has to be done. So you need a reference point in the body. So you have to create a reference point. So on the tools, you are having an option for reference point. So just look at the reference point. Where we going to create the reference point, we will be creating the reference point at the center. So now the geometry is completed. We are having a roller of rigid body and we have created the reference point. Then you are having the sheet and it is defined as deformable and it is 2D. So coming back to properties, So what we need to define? We need to define the properties of the sheet and it is elastic, perfectly plastic. So come here, material manager, create. So material, we are defining the material as material 1 itself. So we have to define the elastic properties, elastic, and it is isotropic. It's isotropic. The next modulus, it is 10,000 megapascal. 1, 2, 3. It's 10,000 megapascal. And Poisson ratio it is 0.3. Then after that, what we are having? We are having plasticity. So what we are going to assume, it is elastic, perfectly plastic. So yield point is 100 megapascal. Remember that stress we are going to enter in megapascal. 100 megapascal yield stress, you will get a plastic strain of 0. Then we will be having a very small increment, 100.1 plastic yield stress. You are going to get a strain of 1. So the material properties is defined. We created the material. And now you have to create the section. So the section you have to say solid homogeneous. So our section is solid homogeneous material. Continue. And what we are assuming now, we are assuming a 2-dimensional analysis. So our analysis will be mainly plane strain analysis. So what we are assuming that the width of the sheet before enter into the roller will be equal to the width of the sheet after passing from the roller. So what we are the analysis which we are going to follow is plane strain analysis. Thickness we can assume it is a default 1. Okay. So it's like we have already created the section which is plane strain. Then you have to assign the cross section. You can assign the cross section. You can assign the section to this deformable body. So section 1 done. So the cross section is assumed. So now we assign the material properties to the sheet. And we don't need to worry about anything about the roller because it's a rigid body. So properties we have done. Now what is the next process? It is assembly. So since we create the roller and the roller as well as the sheet as per the correct geometry, during the assembly we don't need to do anything. We will bring both these items inside the screen. Then automatically it will align in which location what we require. So go to the assembly. So what we are having roller as well as the sheet. So roller and sheet is arranged according to that requirement. So click OK. So it is done. So assembly is completed now. So what is required now? We will go to step. And when we are discussing about the steps, we will move back to the slide. So let's look at what is happening in the steps. In the steps, we will be having 2 parameters. Initially, we will be applying some force. We are having, so your roller is like this. Then your plate is the other way. So the plate is like this. So what we are going to do, initially we have to initiate the contact between the roller as well as the plate, and there should be some normal force between them. So in order to generate that one, we will be applying some force here. So let's say we are going to apply a pressure of 10 megapascal in order to initiate the contact. That is we are going to do in the step 1. That is we are going to define. And step 1, the time we will be having a very small time. It is 0.01 second. And after that, on the step number 2, this is step number 2, we will be applying this rolling process. And when you are talking about the rolling process, what is the speed which is given? It is the speed of the roller is given 150 RPM. Speed of this is 150 RPM, which will indicate that it is actually rotating 2.5 revolution per second. It is actually 2.5 revolution per second. So it's essentially, if you look at the speed in the radian, it is 2.5 multiplied by 2 pi radian per second. So this is the speed in radian, angular velocity in radian per second of the roller. Then how much it is going to come? I'm just counting it. Is 2.5 into 2 into 3.14. So you will be getting around 15.7 radian per second. So the rolling process which we are going to simulate, let's say we are simulating for a rotation of roller for 90 degree. So 90 degree. So which is essentially pi by 2 radian. So how much time it is going to take to rotate 90 degree? So this you can calculate from here. T is equal to 90 degree, it is pi by 2. Is pi by 2 divided by 15.7 radian per second. So how much it is going to come? It is going to come 1.57 divided by 15.7. So which is essentially around 0.1 second. So we will be starting, since I have created around 200 millimeter, which roughly the entire sheet is going to move within 0.05 seconds. So that is the reason I have created 0.05 second. So the time which we will select 0.05 second only in the step number 2, where the rolling process is going to happen. So now we will come back to the abacus. So on the steps, we will be creating 2 steps. Create. So step number 1, what we are going to create, we will be creating static generator. So then time frame for that one is 0.01. So NL geometry is non-linear geometry, that can be switched on NL geometry. So when you are moving to the incrementation, we are dealing with elastoplastic behavior. So essentially the stress strain behavior, material behavior is non-linear. So you cannot solve it by using one increment. That's not possible. So you have to have more increment. So which will be the problem which we discussed in previous, we created always one like that, one like that, everywhere it is 1. But now we are dealing with a problem which is where you are having non-linearity. So then maximum number of increment, 1 is not sufficient. We need to increase the number of elements. Let's say the maximum number of elements is 0.10,000, it's 10,000. Increment size, maybe initial increment size, since we are dealing with 0.01 second, I will take 1 by 10th of that one, 0.001 second. And minimum increment is okay, 10 raised to minus 7, and maximum is 0.01. That is what we are going to take it. So we have created the step 1, which is basically the process of, which is basically the process of initiating the contact. And second step is actually the rolling steps. I name it as rolling process, rolling. So which is following this on after bringing the contact, which is static generator. And what is the time period? It is let's say 0.05. And incrementation, let's say we are having 10,000. Same, we will be creating same. So let's say we are going to have 0.001, and it is 10 raised to 1 into 10 raised to minus 7, and it is 0.05. Okay. Done. So step 1 and step 2 is created. Step 2 is rolling process. And after that, what is the next step? The next step is interaction steps. The interaction step, we need to define the contact between the sheet as well as the roller. So interaction, initially we have to define the interaction properties. So coming back here, interaction property manager, click what we are defining the contact. So click continue. So which type of contact we are having? Tangential behavior, which essentially make the friction. Tangential behavior, we are actually having friction. So coefficient of friction we will be entering here, it is 0.5. Then what we are having? We are having normal behavior. There is normal behavior. So everything is default. So we define tangential behavior with coefficient of friction, and we define a normal behavior. So done. Now what is required now? We need to define the contact surface. So you are having here interaction manager. In the interaction manager, you have to define the, you have to create the surface, create the both surface which are coming in contact, create. So what we need, we will be creating surface to surface contact. Surface to surface contact, we have to start from step number 1. So whenever we are going to apply the force itself, the contact has to become. Default it is coming in step 2, that is a rolling contact, rolling process. But you have to initiate this one in the step 1 itself. Step 1, we are going to create surface to surface contact. Click continue. So which is the main surface? The main surface is the roller surface, which is considered as a rigid body. Generally, the main surface will be taken as wherever it is having rigid body. So we are having rigid body here. So we select that one. This is a main surface. Click done. Then Abacus is asking which surface will be coming in contact. The outside surface is going to come in contact. Then that means yellow it is going to come in contact. Inside is magneta. Magneta is not going to come in contact. Outside is going to come in contact. So what we need to select? We need to select yellow. Then it is asking the secondary type, secondary surface. What we are actually looking, we are looking at the secondary surface, which is the sheet. So just select surface, and we need to select this surface. What we need to select? We need to select only the top surface, and here also selecting this surface. Then by using the shift, you are able to select the two surfaces. So this is the surface which is coming in contact with the roller during the rolling contact. If you look at the other surface, this is never coming in contact, so you don't need to define it. You need to define only the top surface which is coming in contact. Done. And it is surface to surface contact. Everything is default. Interaction property we have already defined. The friction is already defined. Click OK. You can look at this is the top surface of the sheet and the outside surface of the roller, which is going to come into contact. So now look at when you define the interaction property, it is created in step 1 and it is propagated in rolling. So we need this interaction on both steps, initiating the contact as well as the rolling process. So propagation is required. So yes, we have done it. Interaction is done. Then what is the next step? Interaction is completed. What is the next step? It is load. On the load module, what we need actually, on the step 1, we are going to apply a force here. Step 1, we are going to apply a force here. So we will be creating load. So create load. What we are going to create, I am going to create some pressure. Where we are going to create, we need to create on step 1. Now, which location I have to create? The location I am going to create it here. So continue here. I will click on continue here. So Abacus will ask me for the location. Select the surface of the load. Which surface? We will apply the force this surface so that the contact will be initiated. This surface. Click done. So now what is the magnitude? It is 10 megapascal. 10 megapascal. That is a random value which I have taken to initiate this thing. Okay. So the force is going to apply here, which is around 10 megapascal. Now here, when you apply here, this sheet is coming in contact with the roller. Now, when you look at the roller, when you look at this condition, you can see load is defined like this. Load is defined like this. Load is created in step number 1. You can see it is propagated. But remember that this force we are going to apply only in the step 1. We don't need this step in the rolling. So what we are going to do, we will be deactivating this one. On the rolling process. We need this load only in the step 1. We don't need in the rolling step. So I will select this propagated and then I will deactivate. So that means the load is going to apply only in the step 1. Now look at the boundary condition. Look at the boundary condition here. The boundary condition where we need to create, we can create the symmetry boundary condition at the bottom. So at the bottom line of the sheet, we will be creating the symmetry boundary condition. So create. So we call it as, I will just name it as symmetry boundary condition. So what we need to apply displacement. Which is the location? The location is here. What is the displacement constant which you are going to apply? None of the point is able to move up or down. None of the point is able to move up or down. So we will be restricting this U2. U2 we will be restricting on this surface. Click done. So the symmetry boundary condition is required for both. Is required for both step 1 as well as the rolling. So if you look at it is created in step 1 and it is going to propagate it in rolling. So symmetry condition is valid in all the steps. So now what is the next boundary condition you have to apply? Next boundary condition you have to look at the roller. When you look at the roller, what we need in the step 1, when you are applying the force, the sheet is come and contact with the roller and the sheet is going to apply some force on the roller. So what is we require? The sheet should not displace. Sheet is a rigid body. When you apply a unbalanced force on the rigid body, it is going to displace as per the Newton. So you don't want that. So we have to fix it. So reference point, we have to fix it in the step number 1. So all the degrees of freedom, we have to fix it. You should not allow the x-axis movement of the roller, y-axis movement of the roller, as well as the rotation of the roller. All these things has to be prevented. So that boundary condition we will be fixing it. So click on the boundary condition. What we are going to create now, we are going to fix the roller in step 1. So I am just naming it is fixing the roller. So displacement rotation. Continue. Where we want to fix it, we want to fix it. Reference point. Done. What we want? We don't want U1, we don't want U2, and we don't want UR. That means the roller is going to fix at the step number 1 when you apply the force. Done. So this is done. Now if we look at this fixing the roller, we have done it. Let's look at the next boundary condition. Let's look at the next boundary condition. What is the next boundary condition required? Look at the third one. Look at the third one. What is required there? The reference point has to be fixed in the rolling process, but you should allow the rotation. During the rolling process, the roller is going to rotate about its own axis. And the reference point or the center point of the roller should not move because we are fixing the roller by using the bearing. The bearing, if you look at a rigid support, then it is not going to move. So that we will be creating here. So create boundary condition. What we are going to apply? The roller boundary condition. Let's say we are calling it is roller displacement, or we call it as a fixing displacement in rolling. Fixing displacement roller. So when you look at this boundary condition I am going to apply only in the step number 2, where the rolling is going to happen. So step 1, what we need only in the rolling. In the rolling, I am going to apply a displacement boundary condition. Click continue. Then select the reference point. What we need to apply? We need to apply U1 is equal to 0 because during the rolling process, the roller should not move along x-axis and it should not move along y-axis, but it has to rotate. So there is no constraint you can apply on UR3. Okay. What is the next thing which is going to you have to notice now? Because here fixing the roller in the step number 1, we have already done it. If it is propagated in the step number 2, the roller cannot rotate because as per this fixing the roller, everything is fixed in the step number 1 and that is propagated in step number 2, you cannot rotate the roller. So fixing this roller boundary condition, I am going to deactivate. I am going to deactivate here. And that means symmetry boundary condition is going to be propagated in both steps. Fixing the roller, we will be fixing the roller at the center point in step number 1, that will be deactivated. And fixing the roller in the rolling process where we will be constrained only the displacement along x-axis and y-axis. The rolling motion is allowed. So what is the next boundary condition you have to apply? Next boundary condition, you have to apply an angular velocity to the roller. And which step you have to apply? You have to apply that condition on the step number 2, the rolling process only. Then you have to apply the angular velocity. So create what is the boundary condition? We are giving angular velocity to the roller, angular velocity to the roller, angular velocity. We are going to give angular velocity. Which steps you have to apply? We are going to apply the rolling process. Now continue. Where we are going to apply? On the reference point. You can see done. So you can see V1 represent the linear velocity along x-axis. We don't want any linear velocity along x-axis. V2 represents the linear velocity along y-axis. That is also not required. VR3 represents the rotation velocity along z-axis. So now if you look at the roller is going to rotate about z-axis. So VR3 represents velocity, R represents rotational velocity, VR represents rotational velocity, 3 represents the z-axis as per the abacus. So VR3, what we are going to assume, what is the velocity? It is 15.7 radian per second. 15.7 radian per second. That is what we are going to apply. So these are the 4 boundary conditions you have to apply. Let's look at whether the boundary condition is completed. I did not miss anyone. Come back here. So these are the boundary conditions. So the boundary condition which we need to apply a small load on the plate. So we have applied a pressure of 10 megapascal. Then what is roller to be fixed? That means U1 is equal to 0, U2 is equal to 0, then UR3, the rotation about z-axis is equal to 0. Then symmetry boundary condition on the plate. On the plate, at the bottom of the plate, you are going to apply the boundary condition, you are to 0. Then on the step number 2, only displacement on the roller to be constrained. Roller is free to rotate. So U1 there is no constraint, U2 there is no constraint. Sorry. U1 we are going to fix it 0, and U2 we are going to fix it 0, and UR3 we are not applying any constraint. UR3 there is no constraint, no restrictions. No restrictions we are going to make it. And then add angular velocity to the roller, that is 15.7 radian. That means VR3 rotational velocity along z-axis we have given it is 15.7 radian per second. Now symmetry boundary condition of the plate, which will be propagated from step 1. This U2 is equal to 1, which is going to propagate it from surface. Propagated on the bottom of the plate or the center point of the plate. So you are having applied a small load on the plate. We have done it. Roller is fixed. This is so this is first boundary condition. This is second boundary condition. And this is the third boundary condition. And this is the fourth boundary condition. This is actually propagated. So this is the first boundary condition. So this is the second boundary condition itself. So totally 4 boundary condition. You have applied 4 boundary condition. So boundary condition is completed. Coming back to abacus. So now loading is completed. What is next? Next we have to do the meshing. Roller is a rigid body, though there is no meshing. We will move to the part. We need to do the meshing only along the. We need to do the meshing only in the plate. So we will be doing a simplified meshing here. We can create seeding here, seed part. So approximate global size I will call it as 4 for some time. So apply. So it is created. Then. So then you are having an option for meshing. Okay, to mesh the part. So meshing is done. So meshing is done. Now what we require? We need to check the element type. So go to the meshing, element type. So select the region. Done. So what are we going to use it? We are going to use the plane strain element. Look at the option here. So default it is selected as plane stress. We are looking for plane strain analysis, plane strain. You can see the element which is used by abacus. It is CP E4R. You can go to the abacus website and see the degrees of freedom there. And you can see whether we are having sufficient degrees of freedom. The degrees of freedom required is the element should be able to take the x-axis displacement as well as a y-axis displacement. Done. It is able to take it done. So meshing is completed. So now everything is done. Everything is done. What we are going to create, I forgot to create the work directory. We will be creating a work directory. Desktop, FPA. So let's say I will create another folder, problem 3. Sorry, problem 4. Problem 4A. So problem 4A is my work directory. Done. So then what we will do, we will save this work. On the problem number 4, we will save its problem 4. Done. Now we can run the job, create. So the job name I will give problem 4. Click continue. Everything is default. Okay. Now I will submit the job. Let's see how it is going to come. How it is going to come. So it may take some time. So you can see the monitor and you can see whether it is running or not. So somehow it's running. So it moved to step number 2. You can see the total time here and you can see the step time here. So total time is step 1 plus step 2. Step time means the step 2 only. So it's 0.05. You can see it is 0.05. It is reaching the step number 2 and total if you look at 0.06. So Abacus telling that it is completed. Abacus telling that it is completed. Let's see the result. So let's see the result. So you can see this animation. Let's look at the animation. Now it is showing the von Mises stress. So let's see the animation. Then we will be good to see the animation. So let's concentrate on this area. So we will see how it is moving. So when time is increasing, you can see. So now it is a step 1 thing. So still it is step 1. You can see the stresses are being developed. So it is still in step 1. Step 1. So step 1 it is initiating. Step 1. Step 1. Step 1. So now you can see the rollers start rotating. So let's look at here. Let's look at the animation. So you can see this is the animation of the process. So 0.05 is just enough to pass the entire material, which is actually 200 millimeter length. So you can see this animation. So this is how you can create. Just give me a second. So yeah. So now if you look at the circle, which is not as smooth, you are able to see this one. So if you want to make it a smooth option, what we can do, you can go to the view option and you are having this ODB display option. So once you select that ODB display option, you are having curved lines and faces. So refinement level is coarse. So you can just convert this one from coarse to fine or extra fine. So let's look at this one. So you can see it is fine. Click OK. Now you can see the process. So let's look at the animation now. This will be better to see. So just animate. So you can see this is how it is going to come. You can see the roller is going to be rotated. So this process, you can see the animation now. Now what we need to find out, we need to find out the road separating force. Where the road separating force is going to come? Road separating force is going to come on to the reference point. Road separating force is going to come to the reference point. So, but when you look at here, it's a time dependent process. Initially, you are going to initiate a contact, and the second thing, you are going to perform the rolling operation. So it's a time dependent process. So depending on what time you are talking about, the roll separating force can change. Initially, you are just applying the force, the roller is not moving. So when the rolling process is going to be started, this roll separating force is going to come in picture. So basically, the roll separating force will be changing with respect to time, with respect to our analysis. So if you want to find out that one, what we can do that, you go to the tools, then you are having this XY data. So then create XY data, but we need to change this one, 1 minus 6 plus 2. What we are looking, the roll separating force, the reaction force, and what point we are looking? We are looking at the reference point. We are looking at the reference point. The magnitude, we are looking at the total magnitude. So when you look at the roll separating force at a particular point, you can just look at here. So where we need to look at on the nodes, we can look at here. So you can see the roll separating force is around 5,000 at this time, the time which we are talking about it. That the current time is, you can see the step time here, that time it is here. So if you want to see how the variation of roll separating force, go to the tools, XY data, create ODB field output, continue. So we want the nodal point, and where we need, what we need the roll reaction force, and what we need the magnitude. So we need to select the point at which, go to the edit selection and select this point. Done. So now if I ask software to plot, the software is going to plot with respect to time. So just select this one. You can see this is a roll separating force. So you can see roll separating force is actually plotted along y-axis and time is along x-axis. You can see initially we are actually, there is a contact initiation. That's step number 1. Step number 1, you are just applying a small force so that your the roller is coming in contact with the sheet. So during that condition, you can see the force is smaller. And after that, you can see when you are starting the rolling process, you are having an increase in this reaction force. So after that, you can see there is a variation, but more or less it is going to be constant. And now if you look at the roll separating force is around 5,000. So this XY data is also able to, you can able to extract it. You are able to extract from here. Tools you are going to have, then you can edit this one. So you can see these values. So roll separating force is very small initially when the step number 1, which is actually up until 0.1 second. At that moment, you are having 324. And after that, you can see when the time is going to increase, this reaction force is going to increase. So it is going to stabilize around this point. Now, if you look at, so the roll separating force is in the range of around 5,200 or 300 Newton. So roll separating force is around 5,300 Newton. That is the roll separating force which you are going to get it. You can also copy this data and plot it in Excel also. That also you can do. So this is how we can model the rolling process. Thank you. Thank you.